Hey, this video is a summary of our robotics competition we, Mattia and Antoine, have been working on recently. The purpose of the video is to serve as a technical support for us to remember what we worked on and also to showcase our results to people interested in them. We have decided to organize our presentation in the following way. I will first discuss the event and give it a short description, then explain our approach and how we evaluated different technical solutions, then describe what we chose and how our system works. We'll then continue by explaining how the event went and what results did we get, and finish by talking about what could have been better and what's next for us and the project.
And let's start with a presentation of the event and the Self-Racing Car organization, which is an organization that organizes an engineering competition once a year, where the challenge is to complete a lap of a full-sized racetrack and autonomously. In practice, it's not really a race because the cars are going on track usually one at a time, so they're not racing head-to-head, which makes the problem a bit safer, but still super challenging. And in practice, more than a pure competition, it can be seen as 2 days of testing and troubleshooting and collaborating between different people who are passionate about self-driving cars, self-racing cars, and this technical challenge. And this event has a real value because it's one of the few where you can test a self-driving system at the limits of speed and handling, etc. And you can test so self-driving cars themselves, but also sensors, also algorithms. And that means that in practice, in the competition, there are some companies from the self-driving industry, but also some hobbyists. This year, the event took place at a racetrack in California, which is Laguna Seca. We can see it on the right side. It's a very famous racetrack, which is known because it has a pretty high elevation change and a very famous downhill corner called the corkscrew. In the past years, the event was held at a different racetrack in California called Thunderhill. And this year, there were a lot of different participants from different horizons. Some companies who develop self-driving cars, some companies who develop more sensors and also services around self-driving in general, and 2 teams of hobbyists, including our team.
And speaking of the team, our is composed of Mattia, this is me on the left.
And I'm Antoine on the right side of the picture here. And the 2 of us, we met in university about 9 years ago. And now we're both working in the field of self-driving in the San Francisco Bay Area.
Well, let's start by going through our approach, or the approach we took regarding the event. So even though we have known about the self-racing car competition for a while, we only decided to participate about 2 months before the event itself, which gave us quite a tight schedule that guided us, a lot of our decisions. We live relatively close by, which means we were able to meet and work in person on weekends, but still had to split the work efficiently. In terms of budget, our goal was to stay around $500, which means we could buy a bit of hardware for sure, but nothing too fancy. Something that would have been really nice is to have a vehicle platform, something we could ride on, like a small cart, but that would have been a little out of budget for us, or a little too complex to handle. So we decided to stick with something rather small. And the same goes for the self-driving techniques we used. We had to choose simple algorithms using reasonably simple sensors and reasonably computing hardware. And we'll now go through the different options we had for the 3 main aspects of the design, starting with the vehicle platform. So when we started thinking about the options we had in terms of a small vehicle platform, we saw three main options. The first one is to build our own vehicle. It is, of course, what could have offered the most flexibility, but it would have been too complicated to design our own chassis in the 2 months time frame. And here on the top right corner, you can see a very early CAD prototype. The second option was for us to buy an existing RC car and modify it. We know that modifying RC cars to interface with them with custom software is something that other people have done in the past. So we knew it was doable. And that way, there's no need to design a drivetrain, a steering system, or other complicated parts. So in the picture in the middle is one of the RC car model we considered buying. And the last option is to buy an electric skateboard and modify it so we can steer. It's an option that would have allowed more power than the RC car, but the mechanical design aspect would have been also too complicated to get through in the 2 months. So in the end, we decided to go with the second option and buy an RC car and modify it.
Now that we had a vehicle platform, we had to choose what sensor modalities we wanted to use. And the goal of the sensors is to indicate what is the state of the vehicle, so its position, its speed, its acceleration, and also possibly what is around the vehicle. In practice, the format of the event was that we have the cars running on the track one at a time, so we didn't really have to detect other vehicles or other dynamic obstacles. So now we'll run through some of the sensors that we have evaluated, starting with a GPS sensor that can provide the position. And for one that costs around $50, like the one we can see on the picture here, it provides a precision of around 10 meters, and it's fairly easy to interface with, so that's a good option. There are some different kinds of GPS called differential GPS. They can achieve centimetric precision, which is very good, but they're pretty expensive, around $250 minimum, so that's a bit out of our budget. Another famous sensor option for self-driving is the camera. Of course, can be used to recognize what's around the car and also to localize the car in the world. Because we didn't have to avoid things during the event, we decided to not go with a camera. Another staple sensor of self-driving is the LiDAR sensor, which can be used to also recognize the environment by measuring the distance from the sensor to what is around it. For our purposes, and especially the distances that we want to measure, a LiDAR sensor would have been a bit too expensive, so we decided to do without. Another one that we considered is the IMU, or Inertial Measurement Unit, which provides measurement of acceleration that can be used then to derive speed of a vehicle, so something pretty useful. And then two other sensors that we evaluated. The first one was the wheel speed encoder, or wheel speed sensor, that can measure the speed of a wheel and as such help to derive the speed of the vehicle. And same goes for the optical flow sensor. It measures the movement of something in the same way a computer mouse works. So by moving it around, it wouldn't have worked very well in our case because it's not really well suited for the range of speeds that we wanted to achieve with our vehicle. So in the end, we went for a very simple solution, get this sort of GPS to measure the position and the speed of the vehicle. And we also got an IMU in case we had time to integrate it in our system to provide better information on the speeds of the vehicle. And lastly, we needed to decide on the computing platform. Its goal is to process the sensor data and then generate the commands for the self-driving. Here we evaluated 4 options. The first one was to use a laptop. It's an option that would have allowed quite a lot of computing power, but in practice, a laptop is even bigger than the vehicle platform that we had, so we couldn't really use it. Next up was a staple of the robotics projects in general, which is the Raspberry Pi that we can see here in the top right corner. It's a golden standard for small projects with electronics and software, which is far less powerful than one of the laptops that we had. But the good thing is that it's very small and it's not power hungry. So perfect for this sort of small project. We also evaluated the sort of cousin of the Raspberry Pi, which is the Odroid. We had an Android already, the XU4 here, but it's a bit less powerful than the Raspberry Pi that we had, which was the Raspberry Pi 4 with 8 gigs of RAM. And finally, an Arduino, so either Arduino Uno, which is the small model, or Mega, which is a slightly larger model. This one is perfect to interface with electronics and hardware. So it's definitely not powerful enough to run the self-driving algorithms, but perfect to interface with the RC car systems. So in the end, we decided to go with a Raspberry for the self-driving software and an Arduino to interact with the RC car systems. And at this stage of the reflection, we had spent already 1 or 2 weeks on making research and design decisions. So it was time to get down to the implementation, which will be the scope of the next section.
Yes, as Antoine said, let's proceed with diving into more details concerning our design choices and talk about how everything works. And let's start with the vehicle platform, of which we can see a picture here. So the RC car base is a Tamiya TT02, a very common 1/10 scale RC car, which cost us around $100. It has a brushed DC motor as opposed to a brushless motor, which is not ideal for high speed and longevity, but it was good enough for our use case. Adding all of our components increased the weight, so we decided to gear it down by about 30% to get more torque, especially in the long uphill section of Laguna Seca. And we managed to squeeze all the electronics under the stock plastic bodywork of the car and build an extra homemade bumper that you can see here in the picture for when we crash during testing. And on top of the bodywork, there's a GPS antenna as well as a GoPro, which is not used for self-driving, but just to record videos during the attempts. And here's a picture without the plastic bodywork. You can see here the different components in a very prototype like state. This is partially designed like this, as we wanted to be able to assemble and disassemble things as needed. And what we did to make everything fit is to laser cut a small shelf that fits under the bodywork and on top of which most of the components stand. And here's the detailed list of all the hardware we used. Very briefly, without going to too many details, we have the car, the servo to control the steering of the vehicle, the receiver and transmitter. This is our remote control that's used to engage or disengage the autonomous mode and also to transmit the throttle and steering commands. Our GPS sensor, an additional antenna that works with the GPS sensor, a battery, the Arduino Mega, and the Raspberry Pi.
Now that we know how our system looks like, we can dive a bit deeper into the electronics and power architecture. So all of the components we have here fit inside the car, except the ones that are in purple on the left side. The main compute part is divided in two. We first have the main self-driving software that runs on the Raspberry Pi, and then the Arduino at the top interfaces with the actuators, the servo motor, and the ESC and motor of the for the throttle of the RC car. And then in terms of power, we have a lithium battery that powers the two motors, and we have a USB power bank, same as what we could use to charge a phone, that powers the Raspberry Pi. And then on the left side, we have a laptop that communicates over Wi-Fi with the Raspberry Pi to enable us to debug on the go, etc. And then the radio receiver that we can use to drive the car manually when we need to, and also engage and disengage the self-driving mode. And now Mattia will dive into the flow of signals into our system.
Yes, so here on the left side, the purple box represents the radio receiver. So it's a 6 channels, meaning we can transmit 6 signals, but we only use 3, which we read by connecting the Arduino Mega to the receiver. The first channel is used to receive the throttle and brake as a PWM signal. The second channel is used to receive the steering, also as a PWM signal. And the last is just an on-off signal that we use to manually engage or disengage the autonomous mode, also as a PWM signal. So as we briefly mentioned before, there are 2 modes of operation. The first one is manual. In that case, we read the throttle, brake, and steering and send them directly to the servo motor to control the steering and ESC to control the vehicle entirely manually. And the second mode of operation is autonomous. In this case, the Arduino doesn't really listen to the throttle, brake, and steering coming from the receiver. Instead, it receives new commands from the self-driving software that's running on the Raspberry Pi. And on the diagram, the added signal called logging is just used to log data from the Arduino to the Raspberry Pi.
Now that we know about the hardware and the electronics, let's dive into the self-driving approach. We went with something very simple that doesn't really care about the rest of the things happening in the world and just follows a predefined trajectory, which works for this type of event and was already challenging enough. So the idea is to follow the following loop. So first step is to figure out where the car is. And for that, we use our GPS sensor. The second step is to figure out where the car needs to go. And for that, we had a list of predefined waypoints around the track that we wanted to follow. To figure out how to get there, there's some math involved, and we'll present it in a few slides. And the control is split into 2 parts, the lateral control, which is the steering, and the longitudinal control, which is the throttle. Because our car is pretty slow, around 25 kilometers per hour maximum, and the track is very large compared to the car, we could afford to not really care about the longitudinal control. And we just decided to go at a constant speed without slowing down in the curves because the car is small enough. And then once the controls are defined, they need to be sent to the actuators, and we iterate and we iterate and we iterate. We see a bit how it looks here on the this little schematics. So we have the car on the track, a list of waypoints defined around the center line of the track, and at each step of the loop, compute the steering angle. In terms of software architecture, we used ROS, and we have defined a set of ROS nodes and a set of ROS topics which carry the information between the different parts of the software. So first step is to have a node that reads the data from the GPS sensor and publishes it in the rest of the system. Second node is a state estimator, which reads this information from the GPS and converts it into a coordinate system that we call a UTM, which was easier to work with. If we had used the inertial measurement unit that we had, we would have integrated it inside this state estimator node to better estimate the speed. And the state estimator was publishing on a topic called the vehicle state, which contained the position of the vehicle as well as the velocity. Then there was a node called the controller, which was using a file with all the waypoints defined and doing the math that we talked about earlier to compute the vehicle command and send it to the Arduino. In practice, the Raspberry Pi and the Arduino, they were communicating through a sort of bridge over stereo. And that's why you go through this bridge and then to the Arduino Mega, where there was another node that was listening to the vehicle command and then sending it to the motor. And as Mattia said earlier, the Arduino Mega was also publishing some logging information on a topic that was called Arduino logging. Now, diving a bit deeper into each of the components, the first step was to use the GPS. The GPS we had could communicate with it using USB, which was fairly straightforward. We used 2 Python libraries. The first one was PySerial to communicate over the serial port, and the second one was Adafruit GPS, which could be used to retrieve information from the sensor. by default, this GPS, it was providing the data in a format which is called NMEA GGA, which is a standard type of GPS information at a rate of 1 Hertz. But because the car will drive fairly fast, we wanted to have more frequent updates. And that means that before starting all the software, we had a little piece of code that was configuring the GPS to provide the localization information in a slightly different format, which is called RMC. And to do so, we were sending a command to the GPS via the serial connection. This type of command was called PMTK. And that way we could receive the messages with the RMC format, which is a bit more lightweight. And that means we could get a message at 10 Hertz instead of 1 Hertz, which was great. Here on the right, we can see a visualization of the GPS track. So here I was cycling at the middle of the road, and we can see that the GPS track has a slight offset around 2-3 meters, something like this, and it's a bit jittery. But we can see that there are no big jumps between one location to the next, and it was the same during the rest of our testing. There were no big jumps during 2 successive GPS fixes. So at this stage, it had comforted us in our decision to use such a basic GPS because we could afford a small offset because the track is pretty large. The next piece in our software after the GPS is the state estimation. So as said earlier, the goal was to provide to the rest of the system the location and the speed. And so converting it from the format that we get from the GPS into the UTM projection. We chose to go with the UTM projection because it's a bit easier to work in a XY reference frame rather than a latitude and longitude. And in practice, it is precise enough for our purposes. We didn't lose any precision when doing this conversion. Then to generate the list of waypoints that the car would follow, we used Google Earth. The good thing was that we could click in the map around the track and then export the latitude and longitude of the waypoints that we had generated into a format called KML, which is the custom format of Google Earth, and then with a bit of code converting it into UTM coordinates as well. Here we can see how the waypoints look for the turn 2 of Laguna Seca. We had 1 point every 2 or 3 meters roughly, especially in the curves, and then on the straight a bit more distance. We also mapped the edges of the track, but this was just to visualize where the car was. We didn't use the edges of the track for our software.
All right, and now and for the next few slides, I'll discuss the lateral or steering control strategy. The goal of the steering control strategy is to steer the vehicle autonomously on the waypoints. Some of the criteria we had before designing it were the robustness. We want something that's working consistently. We don't necessarily want something perfect because the track is very wide, and even if there's an offset of a couple of meters, it's fine. We want something that's easy to design because of the time constraint, and easy to debug also because of the time constraint, and also not too computationally heavy because of the limited computing resources we have. So some of the options we considered were a technique called pure suite, a technique called model predictive control, which is a optimization-based technique, but much more computationally expensive, and another one called standing control that's pretty similar to pure suite. The lateral control strategy we ended up choosing is the pure suite, and we'll explain how it works in the next slide. And this method has the advantage of being easy to understand and of not being computationally expensive. And here we can see the same layout as earlier. We have the track, our vehicle, which is pointing up, and the waypoints. The first step is to create a circle centered around the car called the look ahead circle. This circle is used to create the point which will be the target. It corresponds to the intersection between the waypoints that are just inside and outside of the circle. And this target point is the red point that you can see on the right here. And now that we know where we want the car to go, we have to compute the steering angle it needs to get there. So the vehicle model we used by the vehicle model used by the pure pursuit method is called the bicycle model. It assumes that for a given steering angle, the car turns in a circle, which means that to drive from the current position to the target waypoint, the car needs to follow the circle that passes by the current position and the target point, tangent to the current car direction. And this is the blue circle here. And from there, we can compute the steering angle. We won't dive into the math right now, but the idea is that with a bit of geometry, we can compute the steering angle based on the radius of the turning circle, so the circle in blue, the distance to the target points, and the wheelbase of the car. We have implemented this in Python, and we're running it at a rate of 10 Hertz. And so in the video that we can see here is the pure pursuit running when the car is at the turn 2 of Laguna Seca. Slowed down a little bit so that we can see what happens. This method has one parameter that needs to be tuned, which is the radius of the look-ahead circle. We'll talk about the values we experimented with later on.
Now let's move on to two small highlights on the rest of our tooling. The first one being related to how we start and run the software. One of the disadvantages of using ROS and ROS nodes is that you need to start each of them, and we had quite a number of them. There's a tool in ROS that is called launch files, where you can launch all the nodes from a single command, but it doesn't give a lot of flexibility to restart individual nodes. So instead, we used a tool called Tmux to automatically open such a window with the multiple commands that we needed to run. So here we see that we had the ROS core, the nodes for the GPS publisher, state estimator, and controller, as well as for the bridge, and then a few terminals just for general purpose like logging or debugging. At the beginning, we were wondering also if we should use a virtual environment or even put all our software inside a Docker. And in the end, we decided to use a Python virtual environment so that we can easily contain all the libraries that we wanted to use, but we didn't need to go with a Docker because we had only a single instance of the software on the Raspberry Pi. Second tooling highlight is how we were analyzing the data after the fact. And for that, we were using a tool called ROSBag, which enables us to record all of the signals happening in ROS on the ROS topics, and then to replay them, which means that we're able to record some of the signals and then test some submodules of the software later on. So as an example, we recorded some GPS data outside by walking with the sensor at the very beginning when we didn't have the car. And then we're able to develop the controller node from our living room using this recorded GPS data.
Next, we'll explain how the event went and what results we got. So we can say that the event was pretty well organized, and we feel like every team got the chance to properly test whatever they came with. In practice, each team got the track for roughly 2 slots per day of 20 minutes each. For the RC cars, it was a bit different though, because we needed to follow the RC car from a chase vehicle that we can see here on the picture, and usually had to start from the pit lane and not from the start-finish line for safety reasons. So we'll now go through the 4 tests we completed, starting by the first one that we decided to run at about 50% of the maximum speed with a pure pursuit look ahead of 10 meters.
And we can see here a video with our small car and us following it in the chase vehicle. As Mattia said, we were running at only 50% over the speed because it was our first run, so we can see that it's pretty slow. But one of the highlights is that it drove mostly on the track, which was great to see. One thing that needed to be improved in addition to the speed was that it cut a bit on the inside of turn 2, which is the hairpin, because probably of the value of our look ahead. For our second run, we improved on two of the things that were not so great in the past run. The first one was to increase the speed to around 70% of the maximum value and reduce the radius of the look ahead circle so that we stay a bit closer to the waypoints and don't cut on the inside of the turn number 2. One thing we did too was to add the GoPro at the top of the vehicle so that we have onboard video.
And to our surprise, it performed a full lap in around 22 minutes, though it needed some manual takeovers to stay on the track in quite a number of occasions. And moreover, there was a bug that caused the car to go in manual mode for a few cycles, almost once a second. In practice, this means it was going full speed, then stopping to accelerate, and this every second for the full lap. And concerning for the third run, we had good hopes because we managed to fix the bug from the past day. We even increased the speed by a bit, but we faced a mechanical failure. The screw that attaches the motor shaft to the pinion gear came loose, so nothing happened. And for our fourth and last run, we decided to go all in and increase the speed to 100% and kept the pure pursuit look ahead to 5 meters.
That means that with the increased speed and the bug from the day before fixed, we were able to drive around 22, almost 25 kilometers an hour. And that means that we did a lap from the pit exit to the pit entry. So more or less a full lap in only 11 minutes. And what was great is that it was with only 2 manual takeovers, which was our best score so far. It was probably better in terms of localization than during the second run because the faster the car goes, the more precise the estimation of the car heading is. So in the end, a very successful last run. Now let's jump to the conclusions and also the next steps that we have for this project. So first, discussing about our expectations and the results that we got. During the testing that we were able to do on a local parking lot, we knew that the car could follow a set of waypoints as long as the GPS signal was pretty good. But the GPS signal quality at Laguna Seca was a bit of an unknown because we couldn't really measure it beforehand. So basically, our expectation was that we would be able to drive slowly around the track, staying in bounds for at least a few hundred meters. And also we expected to have quite a lot of tuning to do because we never got the chance to test at Laguna Seca or on a track that was as wide as Laguna Seca. And overall, as we saw during the last few slides, the event went pretty well. We improved at each attempt, except the third one because of the little mechanical failure. And at the end of the event, we drove for almost a full lap with only 2 takeovers. We were also very happy with our design choices. We went for very basic solutions for everything, but it really did the trick given the time constraints that we were under.
And now concerning the things we could improve, we have quite a lot of ideas. First one would be to improve the state estimation. So the reason why the car was driving off the track sometimes during our attempts was because the GPS was jumping quite a lot. To counter this, we could get a better GPS sensor, maybe even a differential GPS. We could add an AMU and also improve our state estimation algorithms to make them more robust. We could also improve our control strategy. For our purposes, the pure pursuit control was a good enough strategy, but if we were to add more speed, we likely will need to improve the pure pursuit a bit or check out other control strategies.
And when it comes to the hardware and electrical side, we could really work on making it more robust. As we've seen, the third run failed because of some mechanical robustness, which was a shame. And also on the electronic side, we had a lot of wires that could move a bit, etc. So for instance, having a custom PCB would help a lot. And then on the tooling side, we were able to visualize and debug quite okay, but especially our visualization was pretty slow. So if we were able to have better visualization or debugging tools, it would make all the development experience a bit more pleasant. What's next is that if self-racing car happens again in 2023, we'd be super happy to participate again, possibly by implementing a few of the improvements we just discussed.
But there are also pretty similar events that exist that have different formats, such as DIY robocars, where people build self-driving vehicles for indoor racing.
That was all for our presentation of this project. Thanks a lot for following along this little presentation. And if you're interested in checking out the code, you can find it all in the GitHub repo linked here. Thanks a lot.
Thanks.